The ticking sound of a clock is a familiar noise to all of us. But have you ever wondered, what makes a clock tick? Inside every mechanical clock, there are wheel-like components called gears that rotate together in perfect harmony, driving the hour and minute hands. Gears play a crucial role in nearly all types of machinery. In this video, we will delve into the fascinating world of gears, explore various types of gears, and uncover their many applications. But first, let's start with some theoretical knowledge. Essentially, a gear is a wheel with teeth cut along its edge. A gear is defined by two key characteristics: the number of teeth and the pitch circle. The pitch circle is an imaginary circle representing the gear, and when two gears interact, their pitch circles touch to form a perfect connection. The pitch of gear teeth refers to the distance between two adjacent teeth measured along the pitch circle. It is calculated by dividing the circumference of the pitch circle by the number of teeth. For gears to work together, their pitch must be identical, otherwise they cannot mesh properly. Now let's discuss some gear terminology. The gear connected to a power source, such as an electric motor or engine, is called the driving gear. The gear meshing with it is called the driven gear. Between these two gears, the smaller one is called the pinion. Now, let's discuss why gears are used in machinery. Gears serve four main functions in machines. First, they transmit power from the engine or motor to components performing useful work in the machine. Second, they can change the direction of motion. Third, gears can increase or decrease the speed of motion. Finally, they help regulate the applied force, precisely delivering appropriate power where needed. Let's analyze these points in detail to see how gears accomplish these tasks. In machinery, power must be transmitted from the motor to various components. This can be achieved through gears, chains, or belts. Belts utilize friction between the belt and pulley to transmit power between shafts. When the distance between shafts is large, belts are an ideal choice, offering a good balance between cost and efficiency. However, they have a minor drawback. Belts may occasionally slip off the pulley. Chains transmit power through interconnected links that engage with sprockets. Compared to belts, they provide more reliable transmission, with reduced risk of slippage, suitable for moderate shaft distances. Gears transmit power through direct tooth-to-tooth contact, eliminates slippage. When two gears mesh together, the teeth of one gear engage with the gaps between teeth of the other gear. This meshing enables one gear to drive the other's rotation. This is how gears transmit power between them. When the distance between shafts is short, gears are the preferred choice for power transmission, and more efficient than belts or chains. Here is a simple gear mechanism consisting of two gears of equal size. In gear terminology, size refers to the number of teeth on each gear. When force is applied to gear A, it transmits this force to gear B, causing both gears to rotate. However, gear B rotates in the opposite direction to gear A. This example demonstrates how gears can change rotational direction. But what if we want both gears to rotate in the same direction? We can place between these two gears a third gear called an idler gear. This idler ensures gear B rotates in the same direction as gear A. When the rotational axes of gears are parallel, this method works effectively. Now let's examine a different setup involving bevel gears. In this arrangement, the rotational axes of the gears intersect at right angles. Here, the driven gear rotates along an axis perpendicular to the driving gear's axis. This demonstrates another way gears alter motion direction. Now, let's explore how gears change motion speed and the forces they generate. Imagine a large gear with 32 teeth, meshing with a small gear having only 8 teeth. When you rotate the large gear, the small gear rotates much faster. In fact, for every full rotation of the large gear, the pinion will rotate 4 times. This relationship between the rotational speeds of the two gears is called the gear ratio. The gear ratio determines how speed or force is adjusted in the gear system. To calculate the gear ratio, you simply look at the number of teeth on each gear. The gear ratio equals the number of teeth on the driven gear, divided by the number of teeth on the driving gear. In our example, the driven gear has 8 teeth, and the driving gear has 32 teeth, resulting in a gear ratio of 1 to 4. This means the pinion will rotate 4 times faster than the larger gear. But there's a trade-off. While speed increases, force decreases. You sacrifice power for speed. Even though the pinion rotates 4 times faster than the larger gear, it won't have much force. Think of when a car is in 5th gear. It moves very fast, but you can't start a car in 5th gear, because it doesn't provide enough force. You must start the car in 1st gear. 1st gear can deliver high force, but cannot achieve high speeds. Not all gears look or function the same way. Which type of gear is used depends on the specific task it needs to perform, such as shaft orientation or required force magnitude. The most common and basic gear type is the spur gear. These gears have straight teeth. They're used when two shafts need to rotate parallel to each other. They're efficient and easy to manufacture, but they can be noisy, because all teeth engage simultaneously, creating harsh sounds. This limits their use in high-speed applications. A great real-world example of spur gears is the planetary gearbox in automatic transmissions. Due to their clever arrangement of central sun gears and planetary gears, they ensure smooth gear shifting. In a planetary gearbox, both the sun gear and planet gears are spur gears. Helical gears are similar to spur gears, but their teeth are cut at an angle to the rotation axis. This angle means, when two helical gears mesh, the teeth don't engage across the entire width simultaneously. Instead, contact starts at one end, then progresses across the entire tooth face. Compared to spur gears, this makes helical gears operate more smoothly, with less noise. However, helical teeth also generate axial thrust along the shaft, requiring special bearings to handle it. A common application is in automotive transmissions. Car transmissions use sets of helical gears. The transmission takes power from the engine and delivers it to the wheels, propelling the vehicle. Herringbone gears are essentially double helical gears. On the same gear, its teeth are inclined in opposite directions, forming a herringbone-like pattern. The advantage of this design is, it eliminates the axial thrust generated by single helical gears, thus eliminating the need for thrust bearings. Herringbone gears are commonly used in heavy machinery, when you need to transmit motion between non-parallel shafts. Bevel gears are typically used. These gears are conical in shape, with teeth cut on the conical surface. They can connect shafts at any angle, but are most commonly used when shafts intersect at 90 degrees. A common application of bevel gears is in automotive differential systems. There, they receive power from the engine and transmit it to the vehicle's wheels. The differential mechanism allows tires to rotate at different speeds. This is particularly useful when the vehicle turns. In some cases, gears need to be installed in confined spaces. Internal gears are designed with teeth on the inner surface of a ring. This makes them highly suitable for compact designs, such as the planetary gears used in automotive automatic transmissions. In planetary gears, the outer ring is the internal gear. The pinion meshes with the rack. Or vice versa, a rack and pinion system is used. It consists of a circular gear, a pinion meshing with a straight tooth rack. When the pinion rotates, it drives the rack, thereby generating linear motion. Its ability to convert rotational motion into linear motion makes it ideal for vehicle steering systems. Turning the steering wheel rotates the shaft connected to the pinion. The pinion engages with the rack. The rack is a straight rod with teeth. When the pinion rotates, it pushes or pulls the rack left and right, thereby moving the linkage connected to the wheels, causing the wheels to turn. For shafts that are non-parallel and non-intersecting, typically between shafts at a 90-degree angle, achieves very high reduction ratios. Worm and wheel are often the preferred solution. A worm and wheel set consists of a worm that resembles a screw, and a wheel that meshes with the worm. For each rotation of the worm, the wheel advances only one tooth, thereby significantly reducing speed. Many worm and wheel mechanisms have a unique feature, called self-locking. This means the worm can easily drive the wheel, but the wheel struggles to drive the worm in reverse. This acts like a built-in brake. However, due to significant sliding friction between the worm and wheel teeth, worm and wheel systems are generally less efficient than other gear types. They are commonly used in applications such as cranes, conveyor systems, and fine-tuning mechanisms. So, next time you see a machine in operation, remember that inside it, tirelessly work these marvelous gears. These seemingly simple tooth wheels are a testament to human ingenuity.